All right, so this lesson will be an introduction to the photoelectric effect. So the photoelectric effect is when you shine light on a piece of metal, sometimes electrons come off of the metal because of the light. When that happens, it's called the photoelectric effect. So this is a setup. If you wanted to do photoelectric effect in the lab, you might use an apparatus that looks kind of like this. So the black rectangle is a glass tube with nothing inside of it, no air or anything else. That's what we call a vacuum. Inside there we have a couple of metal plates or metal surfaces. So this one here is what we're going to shine the light on. It's what we call the cathode. And over here we have another metal surface. That one is called the anode. The cathode and the anode are connected together by a wire, and when we shine light on the metal, sometimes electrons get ejected, so electrons are freed from the metal. And if electrons are freed, they travel across from the cathode to the anode, and they go through this wire here. And in the wire, we've hooked up an ammeter. Okay, if electrons are flowing, there's going to be a reading on the ammeter, and then we know the photoelectric effect is happening. If no electrons are flowing, because maybe the incoming light isn't energetic enough, then the reading on the ammeter would just be 0, and that would tell us that nothing is happening. By the way, this incoming light doesn't have to be visible light. It could be ultraviolet light or infrared light or something like that. So the big idea, the reason that we study the photoelectric effect is that the photoelectric effect can only be explained if you model light as a stream of particles called photons. So the photoelectric effect is famous because it showed that light is a particle. So what is a photon? Okay, you can think of it as a bundle or packet of light energy, or in other words, it's a particle made of light energy. So it's a special particle that doesn't have any mass. It's just energy. Okay, and photons move at the speed of light. So they move at 3 times 10 to the 8 meters per second in a vacuum. And it doesn't matter if it is X-ray photons or visible photons or radio photons. If they're in a vacuum, they are all moving at the same speed, the speed of light. So if we want to calculate the energy of one single photon, we have a formula for that, and it looks like this. Capital E equals HF. When we write capital E, that means the energy of a photon. Okay, H is what we call Planck's constant. There are 2 different versions of Planck's constant. The difference between them is the units. So if I want to calculate a photon energy in joules, I use the top version. If I want to calculate a photon energy in electron volts, I use the bottom version. And then F is the frequency of the photon measured in hertz. Don't forget that you can always convert between frequency and wavelength using this formula here. C is the speed of light. So we could replace F with C over wavelength, which is where this formula came from. So this one here is another way of calculating photon energy. So here we have our electromagnetic spectrum. As we go down the list from radio to gamma rays, the frequencies are getting larger and larger. We just learned that the frequency of the light is directly proportional to the light's energy. So as frequency gets bigger, energy gets bigger as well. So gamma photons are more energetic than radio photons are. And what I'd like you to notice here is in the visible light portion of the spectrum, red photons have less energy than violet photons. And we can also state the relationship between energy and wavelength. It's an inversely proportional relationship. So as wavelength goes up, energy goes down. So in the particle model of light, light has 2 properties. The first property is energy, and we just learned that that depends on light frequency. The second property is the intensity, which is the same thing as the brightness of the light. And this depends on the number of photons. So say you have a lamp that gives off 10,000 photons per second, and someone else has a lamp that gives off 1,000,000 photons per second. The second lamp is going to be much brighter than the first. So in the particle model, energy and intensity are independent, which means that you can change one of them without affecting the other. So, for example, let's say I'm working with red light and I decide to change the light from red to violet. Well, when I do that, okay, red light has a lower frequency than violet light. So red light has less energy, violet light has more. So I've increased the energy of the light, but I didn't touch the brightness, okay? So the intensity of the light didn't change. So the red light and the violet light are equally bright. Or I could do the opposite. I could keep using red light the whole time, but make it dimmer. So because there was no change to the frequency, there was no change to the energy, but the intensity went down. I've got an analogy here, which I'll put the link to that on D2L if you want to go in and read that on your own after. So if we're going to visualize the photoelectric effect, here's what we've got. So we've got a piece of metal, so this would be our cathode, and let's say that it is gold. Okay, in this piece of metal, we have a whole bunch of gold atoms, and those gold atoms have electrons in them. Some of those electrons are going to be close to the surface here. Those are the ones that we care about. If I shine light on the gold, photons from that light are going to come in, and some of them are going to hit the metal. Okay, if the incoming photon has enough energy, it can actually knock this electron off the piece of metal. So to see what's going on, we need to define a couple more things here. So there's something called the work function, which has symbol W. Work function is a property of the metal itself. So gold has a different work function than silver, which has a different work function than aluminum. And you can think of this as how sticky the metal is. So some metals really hang on to their electrons well. Those guys have a high work function. Other metals hold on to their electrons in a weaker way, and those have a low work function. But you can think of the work function as the minimum amount of energy needed to remove one electron from the metal. And then we also have this property here called threshold frequency. The symbol for that is F with a little 0 next to it. This is the minimum frequency of the light that will cause photoelectric emission. So it just means if you go below the threshold frequency, the photoelectric effect doesn't happen. You have to be at the threshold frequency or higher to see the photoelectric effect occurring. So let's say we have a particular metal, and this metal has a work function of 10 electron volts. So what does that actually mean? So the electrons are currently bound to the surface of the metal, or they're stuck there. If you want to unstick an electron, if you want to free it from the metal, you have to give that electron 10 electron volts. We call this overcoming the work function. Okay, to overcome the work function, you have to input 10 electron volts of energy. And if you do that, the electron will be freed and the photoelectric effect will happen. So that means the energy of your incoming photon has to be at least 10 electron volts. So it can be bigger than 10, but not less, or you're not going to see the photoelectric effect. So remember, photon energy is HF. So if we say here, if we say W is the minimum photon energy, then we can calculate that by doing HF, but it's not just any F, it's specifically the threshold frequency. Okay, so W is equal to H, which is Planck's constant, times the threshold frequency. The other thing to know about the photoelectric effect is that it's all or nothing. So either the photon has enough energy to free an electron, or it doesn't. There's no in between. If the photon has enough energy, the electron will absorb the photon, and that means the photon goes away. It disappears. Okay? If this happens, one electron is released per photon. And so if I shine 5 photons on the metal, I should get 5 electrons coming off the metal. It's a 1-to-1 ratio. On the other hand, if the photon does not have enough energy to free the electron, nothing happens. The photon just bounces off the metal, it doesn't get absorbed, and off it goes. Okay, it is not possible for the metal to absorb half a photon or a quarter of a photon. Either the entire photon gets absorbed or none of it gets absorbed. There is no in between. So let's say we have a situation where we have incoming photons, and these photons carry 12 electron volts of energy, and they are landing on a metal, and this metal has a work function of 10 electron volts. What happens? Well, first thing to ask yourself is, will we get the photoelectric effect or not? And the answer is yes, we will, because here our photons have more than enough energy to overcome the work function. So that's great. So of the 12 electron volts that the photons have, 10 electron volts are going to get used up by the work function. Or in other words, 10 electron volts will be used to free the electron from the metal surface. You're going to have 2 electron volts left over, therefore, and those 2 electron volts have to go somewhere because of conservation of energy. So they actually become electron kinetic energy. And that is what this says here. You can pause the video and read it if you would like. But really, right, 12 is equal to 10 plus 2. That's where this formula up here comes from. The energy of the incoming photon equals the work function plus the kinetic energy that the electron has when it leaves the metal. Now, often we will just write this as E without the word photon next to it. And over here, we'll just write this as EK without the word electron next to it. And it's the same thing. But you should also be aware this formula is not on your formula sheet. You just have to memorize it. So a little bit more theory, and then we'll get into some numerical examples. So what happens if we are doing photoelectric effect experiments and we first shine bright light on the cathode and later we shine dimmer light on the cathode, but we don't change the frequency, and so it's violet light over here and it's violet light over here still. Well, you're going to get more electrons flowing. Why is that? Well, brighter light means more photons. And since each photon releases 1 electron, if we have more photons, we also get more electrons. Okay, photocurrent just means current. It means a current that came from the photoelectric effect, but it is just a current. Current depends on the number of electrons. So if you have more electrons flowing, your current is going to go up. So you have to know, if you increase the light brightness, as long as you're above the threshold frequency, the current is going to get bigger. Okay, however, changing the brightness of the light does not change the kinetic energy or the speed of the electrons, and that's because brightness has nothing to do with energy. Remember we talked about that earlier? So what will happen is, in this situation here where the light is bright, we're going to have more electrons. In this one over here where the light is dim, we're going to have less electrons, but where the light is bright and where it's dim, all of the electrons are traveling at the same speed. Okay, what if we do the opposite? So what if we start out with red light, which has a low frequency, and we change it to violet light, which has a high frequency, but we don't change the brightness of the light. So these 2 light sources are equally bright. Well, we can kind of see mathematically what's going on. So remember this formula, E equals W plus EK. Let's just say that red photons have 10 electron volts of energy and violet photons have 15. I don't think those numbers are actually accurate. I just made them up for the sake of this example. But remember, because the red light has a lower frequency, that explains why it has a lower energy, right? Now, the work function of the metal is the same either way, because work function is a property of the metal, so it's not going to change just because I change the color of the light. So let's say this particular metal has a work function of 3 electron volts. So either way, 3 electron volts is going to get used up to free the electrons, and whatever is left over is going to become kinetic energy. So the electrons that are freed over here from the red light are going to be traveling slower, and the electrons that were freed by the violet light are going to be traveling faster because they have more kinetic energy. So what you should take away from this is when you make the frequency bigger, the electrons are going to move faster due to the increase in kinetic energy. However, you don't have any more of them. They're moving faster, but you don't have more electrons than before. So your current is not going to change because current depends on number of electrons. So you're going to do this example here. So go ahead and read it, pause the video, and come back once you've read it. So part A, we're calculating the kinetic energy of the electrons in electron volts. So to do that, we're going to just use our formula here that we wrote down earlier. E for the photons equals the work function of the metal plus the kinetic energy of the electrons. I've just gone in and rearranged for EK, and then I've solved that, and I got 1.18 electron volts. Part B asked us to find the speed of the electrons. Now, it's really important to remember, whenever you are calculating speed, you have to work in joules, not electron volts. So electron volts and joules, they're both just energy units. It's kind of like you can measure mass in kilograms or you can measure mass in pounds. Either way it's mass, but the units are different. Similar idea here. And you can convert between electron volts and joules using this conversion factor, which is on your formula sheet. So here, to find speed, first thing that I did is I converted electron volts to joules by multiplying by the conversion factor. And that gave me 1.888 times 10 to the negative 19 joules. And that's a kinetic energy. So to turn it into a speed, I've just rearranged the formula here. And notice that the mass is the mass of an electron, because this is the kinetic energy of electrons. So that's why I'm doing that. Okay, again, read the example. Come back when you are done. So here we've got a photon. We're being given the frequency. We're being given the work function of the metal in joules this time, unlike in the previous example where it was in electron volts, but it is still a work function. And like before, we're being asked to find a kinetic energy. So I started with the same formula, E equals W plus EK. And then I remembered that E is the same thing as HF. So over here, I've just replaced E with HF, and then I rearranged for kinetic energy. Now, you see Planck's constant, that's what H is showing up here. So I have to make a decision. Do I use the version of Planck's constant that has joules in it, or do I use the one with electron volts in it? Well, because they're giving me the work function here in joules, that means I want to work in joules everywhere in the question. So you'll notice here where I plugged in for Planck's constant, I use the version that has joules in the units. So there's my work, and for my kinetic energy, I got 1.0 times 10 to the negative 19 joules. Okay, last example, it says a graph of kinetic energy as a function of frequency for a photoelectric effect experiment is shown. Identify the slope, the y-intercept, and the x-intercept. So here we've got kinetic energy of the electrons on our y-axis and frequency of the photons on the x-axis, and there's the graph. So you'll notice the graph actually starts right here, okay, but we've extended the line back just to see where it crosses the y-axis. The reason that this line doesn't start from the origin is that, remember, you don't get electrons flowing right from the very first frequencies. Instead, you only get electrons once you've met the threshold frequency. And so the x-intercept right here, this is actually the threshold frequency. Because below the threshold frequency, no electrons flow. Above the threshold frequency, they do. So we've just answered this part here with the x-intercept. Now, to do the other two parts where we identify the slope and the y-intercept, we have to do that stuff where we match a graph to y equals sx plus b. So let's start by writing down our physics equation. So E equals W plus EK. And because we have F here on the x-axis, I'm going to write E as HF, just so this variable actually shows up in there. So remember, whatever is on your x-axis, that has to be your x variable. So it's F on the x-axis. So I'm just going to circle that and identify that as x. And whatever is on the y-axis has to be your y variable. So EK is y. Okay. Now, when we're matching stuff to y equals sx plus b, y is always isolated. So we're going to take the equation here and we're going to make it so that EK, our y variable, is by itself on the left side of the equals sign. So that's what I've done. So EK and then HF minus W. So now, okay, EK is y, F is x, that didn't change. Remember from earlier in the course, whatever variable is multiplying x, that is your slope. So because h is multiplying f, the slope of this graph is Planck's constant. Okay, so that's interesting. It doesn't matter what type of light you're using. It could be ultraviolet light, it could be red light, it could be green light, doesn't matter. If you use it to make a graph, the slope of that graph will always be the same. It will be Planck's constant. Okay. All right, so we've identified the slope and the x-intercept. Now we need to do the y-intercept. Hopefully you can agree that we could write this equation here this way. We could put a plus sign and then write negative w. It's the same thing. The reason I'm doing that is because up here we have sx plus b. So whatever is being added on, that's b, and b is the y-intercept. So b is negative w. So just to explain what I mean by that, let's say that the y-intercept of the graph is negative 8, right? That's the y-intercept right there. That means that negative 8 electron volts is negative w. Or, cancel the negatives, w itself is 8 because the work function can't actually be negative.